a silicon crystalline structure by process like Czochralski method, right? But there is another way how we can get a crystalline material, which is not where you have to melt everything and do the whole process. That process is called epitaxy. So today I just wanted to talk about how do we get crystalline materials and what are some steps involved, right? Epitaxy is another process where we can, if we have crystalline material already, we can grow more crystalline material on top of that. You have to pick up specific words that I use. I'm using the word grow here because what we are doing is we are not uh, pulling out a chunk or a cylinder of silicon or crystalline material. But what we are doing is, if we already have a wafer, we are growing another crystalline material on top of that, right? So makes our life much easier that you don't always have to go back and buy a new wafer. If you have a wafer, you can grow different materials on top of that. And the process is called epitaxial growth, or in short, we call it epi or epitaxy. All right, so if that's the definition. The growth of a thin crystal layer on a wafer of a compatible crystal. The compatible, why do we use compatible? There's a couple of things which would make a wafer compatible or not. Number one, we want to have a similar lattice structure on the lower material because that's going to serve as the seed for whatever we are going to grow on top of that. Right? So if I have a wafer whose crystalline structure is way different than what I want to grow, yeah, it will not happen, or there will be lots of defects, which will not be good for my device. So we need to have a seed crystal on which new crystalline material will be grown. Now, why it has to match? Because once you grow something on top of that, we want the new thing to have same structure and same orientation. I cannot force it because remember, lattice constant, every material has specific lattice constant. So what I'm trying to grow, I know what lattice constant it would have, and I know the what's below. So we need to, if we don't match these things, the crystal that grows will not be good. It will have defects in it. So we need to maintain uh, the crystal structure and orientation. We will get that in whatever we grow on top of that. Now, another benefit of why we are doing epi and not melting everything, because we can do this process at much lower temperature, right? So, which means we can save lots of money. You don't have to heat up things. So, in industry, they sell lots of epi wafers where the material that's available on the surface has been grown epitaxially, or the process done what you call epitaxy. Okay, how is it done? So we do process called chemical vapor deposition. I'll get into that, but there's another thing I want to talk about is we can have many different variations of a material when we do epitaxy. When we do like Czochralski method, you can have one material which is in the molten pot, and or maybe you can add some dopant into that, right? But you cannot have variation in the structure or variation in the material. Let me show you next slide, then this thing will become clear what I'm talking about. All right, question. There's lots of new things, new ideas, new concepts. So talk to me where if something is way off or something is too much out of grasp.
I don't know if it's the same thing, but I remember at one point when they started selling for the phones, the screen protectors, and then it said that it had it was able to what's that word? Like fix itself, like repair itself.
Self-healing, self-healing,
Yeah. Self healing.
scratch resistant or scratch healing.
Yeah.
Okay, yeah,
Yeah, I remember when that first came out, and I thought that was like a gimmick, like try to sell their product. But then I started realizing, oh, this is a real thing, and that was just an eye opener.
right, right.
Yeah,
But that probably wouldn't be crystal because crystalline structures would be very expensive.
no. But it was like something similar, like something like along the lines that it reminded me of.
Right. So, yeah, if I can think of maybe there was some chemical that can react with oxygen maybe and grow another layer. If you scratch the top layer, maybe it was oxidizing and growing another layer. Silicon dioxide is nothing but glass, right? So yeah, you never know what was in there. But
Yeah.
epi or crystalline growth is what would make things very expensive, right? So hence this process is because it requires certain temperature, certain vacuum, and pure material to do this. All right, very good. Questions, comments? All right, I'm gonna keep on going if you guys have no question. It's okay, don't worry. You can ask me question even here or there's this muddiest point forum there as well. Now, I just said that in when you melt something, you can just have one kind of material, right? Silicon or maybe gallium arsenide or whatever, uh, maybe uh, two material we are growing, we can do that. But with epi, remember we looked at this example where we were saying we could change the relative amount of materials. We can do that with epi. We can grow one material in that same machine during the same process. Maybe we put down a crystalline layer of gallium arsenide, and then maybe we put another layer of aluminum arsenide. Okay, why am I talk? What did I just say? There is a reason why I just said that. I said I can put down a layer of gallium arsenide, right? Which falls here, and if I put the line, this is the lattice constant for that material, right? What it would be 5 point, this is 5.7, this should be 5.65, right? Around 5.65, more or less. Then I can put on top of it this material. This has a very similar lattice constant. If I were to draw the line, this would fall somewhere very close to that, right? You see that the x-axis is lattice constant. Are you with me on this? Why lattice constant is important? Because that tells us how close the atoms are from each other. So if you put one layer of two atoms which are maybe this distance apart and you put something on top of that which is bigger distance apart, there's going to be a problem. We'll see that problem in the next line. But I want to show that with epitaxy, we can put down number of bunch of different materials on the fly during the epi process. That's I showed you this before, but that was there. I wanted to talk about how we can put binary or ternary or quaternary materials, and how that would change the wavelength of the band gap. But here, all I'm telling is that how we put these materials down is by this process called epitaxy. Okay, now if you think of lattice constant, the thing that tells us how closely apart atoms, here are the materials grown which may have different lattice constant. So the left side is all okay. Okay, so up to here we had silicon, and then we put down another material which has similar lattice constant. Maybe not. because what you see is this side is longer, this side is smaller. So what it's going to do is going to put some pressure. It's going to find its distance, the interatomic distance. And if you now look at it, this layer is showing a stress because ultimately the material that you put on top would relax and find its lattice constant, whatever it's supposed to be. Yes, this is a very physical thing that we are talking about. I'm not talking about uh, any electronics or anything. If you think about it, if you're making a wall in your home, for example, and you use a brick which is 2 inches wide, so you put 4 bricks, and now you get bricks which are 2.5 inches wide. We want the bricks to be of the same size so we can make maybe zigzag on top of crisscross so we can build a wall with uniform size. But if your every brick is of different size, you're going to end up with something like what is shown on the right hand side. But sometimes we do that intentionally because we want to grow a different material with a different lattice constant. Now, this is what is called lattice mismatch. This is the keyword which is given here. And I can always ask that how can you get lattice mismatch? What process can you use to grow a material that has a lattice mismatch with the material that's below? We use epitaxy for that. Now, how do we do this? There are a couple of machines or approaches how we do this. So one machine is where you would have a reactor where you have a barrel which is rotating and you put your wafers on that and you introduce the gases that would react and create the material, whatever you want to put on the surface of your wafer. So that's one way you can do that. It's called barrel type reactor. Another way how you can do that is what is called molecular beam epitaxy, MBE. That's a very uh, expensive machine. Lots of physics people, they have epi machines in their labs. What you do is you basically melt the material in a vacuum chamber. So this, what you see, it says shutters. So you have molten those, but you have put shutters so they cannot escape their respective containers. But if you remove one shutter, say you remove this, then silicon atoms would start flying because you would have applied a voltage across these two sides. So they would, under the voltage, they would start traveling and they would hit the substrate and they would start gathering one atom at a time and they would start creating a crystalline structure over there. So this is what we call molecular beam epitaxy. Now, if you want to create another, you want to maybe put gallium arsenide, so you would close that shutter and you would open this and this shutter. Equal number of atoms would start flying and they would start making another layer of material, crystalline material on top of the substrate that's below. Now, if you want to change the proportion, you want to introduce aluminum also, you would open some of aluminum. So how much shutter you open will give you that respective uh, respective amount of the material, like wherever you want to be. Maybe you want to have some combination of indium gallium arsenide. So that would depend on how much shutter do you open, right? So I'm just going through the introduction of those processes. There's much more detail that's in the book on these processes. But the end goal is that we want to create very thin layers of crystalline material with different properties, different amounts of different materials, which would result into different lattice constants, different band gap energies, and different wavelengths. So essentially, what we achieve in this process Epi is we can have variety of material deposited on one single substrate. So here what we are it is showing is alternating layers of gallium arsenide and aluminum gallium arsenide. So you are literally looking at atomic layers. So each thin layer is 4 atom thick. So think about it. I showed you atoms before. Today I'm showing you layers of atoms as well in this picture, right? So basically at the end of the day, the most important thing is that we can evaporate different materials with a very precise atomic precision, and hence we can get different wavelengths coming out of those different layers. When we talk about wavelengths, we're talking about optical material, optical detectors or optical emitters. So here's an MBE machine with all those associated pumps and controllers and whatnot. All right, so let's stop here. I will be posting a micro lecture on the last article of chapter 1, wave propagation in a medium, but that will not be part of the first exam. We will have everything up to this point in the exam. Question?
How is the exam going to work?
So it will be on Blackboard, but you'll have to use that responders thing to do whatever it asks you to do, which I think you cannot look right and left. You cannot open another window or things like that.